Today is August 12th, and this is the beginner integral from DailyIntegral.com. So let's start. So we have the integral from 0 to pi over 2 of 2 cosine of x over 3 cosine squared x plus 4 sine squared x dx. So let's start by simplifying this 3 cosine squared x plus 4 sine squared x first. Well, we know that cosine squared x, right, plus sine squared x is equal to 1. So we have this identity, and we can apply this right here. So we'll get 2 cosine x over 3 cosine squared x plus 3 sine squared x is going to become 3 plus sine squared x dx. Now we'll move to doing a substitution for this integral right here. So we can take t to be equal to sine x. Clearly it looks like we have a sine squared x, so substituting in a sine x is going to help us get rid of that cosine of x and simplify this down to a rational type function. So let's do that. So we have dt is equal to cosine of x dx. So we get this integral. Well, what are our bounds now? Sine of 0 is 0, sine of pi over 2 is 1, 2 cosine of x, well, cosine of x dx, so we get dt. We're left with a 2 on top, 3 plus b squared. So now for this integral, we're going to use the fact that the integral 1 over x squared plus a squared dx is equal to 1 over a arctan x over a. So here we have a similar form. We have the integral from 0 to 1, 1 over d squared plus root 3 squared dt. So there should be a plus c here. So what is this integral going to become now? Well, we'll have 1 over root 3 arctan of t over root 3. And remember, we had this 2 right here, so multiply this by 2. And we need to plug in our bounds from 0 to 1. So we get 2 over square root of 3 arctan of 1 over root 3 minus arctan of 0. Well, arctan of 0 is just 0. Arctan of 1 over root 3, well, this is from the unit circle, and we know that when does tangent equal 1 over root 3? Well, that's at pi over 6. So this is going to give us pi over 6. So we get 2 pi over 6 root 3, which is the same as pi over 3 root 3. And so we are done. Now we can move to the easy daily integral from today. So this is apparently very interesting looking, right? We have a sine inverse right here. We have a rational term here. We have a root 1 minus x squared, which is quite interesting. And then we have a sine in our bounds. So clearly this is going to have to do something with sine. We know that cosine squared x plus sine squared x equals 1. And this implies that 1 minus sine squared x is equal to cosine squared x. So if we plug in sine x, right, if we make x to be like sine of t, then we can simplify this bottom part as well as this top part here. So let's try to do that. So we'll have we'll have x to be sine, let's say theta. So we'll have the integral. Well, now we need to switch our bounds. But remember, we're looking in terms of x. So we have 0 equals sine theta. So this means theta is from 0. Then we have on top, well, we have sine theta is equal to sine of 1. So 1. We have e sine inverse of sine theta. Well, that's just going to leave theta. We have plus 1 over root 1 minus x squared. So we have root 1 minus sine squared x equals cosine squared x. So root 1 minus sine squared t, and then of course we need to find our dx. Well, dx is equal to, what is the derivative of sine theta? Well, that's cosine theta d theta. So we have, this should be a theta. We have cosine theta d theta. Well, from here we have 1 minus sine squared x equals cosine squared x. So we get e to the theta plus 1. Since we're taking the square root, cosine squared theta is going to become cosine theta, cosine theta, cosine theta, d theta. The cosine thetas cancel out. And we get the integral from 0 to 1, e to the theta plus 1 d theta. This we can integrate. The integral of e to the theta is just e to the theta. The integral of 1 is theta, 0 to 1. So we get e to the 1 plus 1 minus e to the 0 plus 0. Remember, we can't just take away the 0 term yet. Sure, theta is going to be 0, that is nothing, but e to the theta is not going to be 0. So we get e to the 1 plus 1 minus, what's e to the 0? Well, that's 1. So we're left with e as our answer. Let's now move to the medium integral for today. So we have a very interesting looking expression. We have a cosine, we have a sine, then we have this root x, right? This is from 0 to infinity. So first let's deal with this root 2x here by doing the substitution t is equal to root x. So we get dt is equal to 1 over 2 root x. And so we get the integral from 0 to infinity. Our bounds aren't going to change. Cosine of t squared plus sine of t squared. And then we have a 2. We need a 2 at the bottom. So we have a root 2. So we can make this 1. Take our root 2 in the numerator. So we can just take it outside. Get dt. So we now have root 2, the integral from 0 to infinity, cosine of t squared plus sine of t squared dt. So these two integrals are actually very special, right? These are Fresnel integrals. And these have a known value. But before we talk about that known value, let's try to figure it out ourselves. So let's motivate our solution by first observing that e to the I x squared is equal to cosine of x squared plus I sine of x squared. So this is just Euler's formula, right? Instead of x, we put x squared. And notice that cosine of t squared, cosine of x squared, sine of t squared, sine of x squared. So instead what we're going to do is we're going to find the integral from 0 to infinity of e to the ix squared. But e to the ix squared, does that even converge? Well, instead, we're going to look at a related integral. We're going to look at e to the negative k minus I x squared dx, and we'll call this j. And at this integral, we can show we'll be able to converge. Why? Well, e to the negative kx squared times e to the I x squared. We take the modulus, we'll get e to the negative kx squared. So for k greater than 0, this is going to converge, right? This will very clearly start converging. So this is what we need to do. We're going to find the value of this integral, and then we'll take the limits as k goes to 0 from the positive. So this is what we're going to do. This is our plan. So let's do this now. Well, let's start by evaluating this integral. This is it looks related to the Gaussian integral. So we're going to use a similar strategy. We let j squared, and we're going to now convert this into polar coordinates. So we have e to the negative k minus I x squared plus y squared dx dy. And now we make this into polar coordinates. So we have our double integral. We have e to the negative k minus I r squared dr d theta, and we need our Jacobian, so we have an r. Now let's think about what our bounds are going to be. So our bounds for r, Well, x squared is y squared equals r squared, right? We know x is from 0 to infinity, y is from 0 to infinity, so r squared, right, or r can be from 0 to infinity. Okay. Now next, what is theta going to be? Okay. Well, again, let's think about this. We know that x and y are positive. This means theta has to be from 0 to pi over 2. And you can see this by looking in the first quadrant and seeing what angles that produces. So we now have this integral. And we can actually split this part into two parts, 0 to pi over 2. D theta, integral from 0 to infinity, e to the negative, k minus I, r squared, times r dr. So this is going to give us pi over 2, right? And this integral, it can be solved by a pretty easy substitution. So let's just look at what we get. E to the negative k minus I, r squared over negative 2 k minus I. And again, from 0 to infinity. So we now have pi over 2. Okay, so, right, and now what are we going to get? So as this goes to infinity, e to the negative k minus I r squared. So r goes to infinity. This is going to come arbitrarily small, very, very small, right? So small that we can now say it's going to go to 0. Now let's look at our next part. Well, now we put r squared. Well, we have r equals 0, so this term on top is going to become 1. So we get 1 over, and the bottom part we just don't change. So we have negative 2 k minus I. So let's simplify this. We get pi over 4 k minus I. And now what do we do? Well, we want j squared. Let's go to pi over 4 times k minus I. We take the limit as k goes to 0 from the positive of pi 4 k minus I. And this is going to be pi over 4 times negative I. So this is pi I over 4. Okay, but this is j squared, remember. So j squared is equal to pi I over 4. So what we want is j, okay? So how can we do this? Well, j is going to be square root of pi over 2. And we are going to write e, we're going to write I as e to the pi I over 2. Which means, we just multiply this by 1/2, so we get root pi over 2 e to the pi I over 4. Here again, you can use Euler's formula again, and it's going to be pretty easy to calculate that, so I'm not going to spend time on that step. We're going to get this, okay? We'll get root 2 over 2 plus root 2 over 2i, and we can now simplify this. So we're going to get square root of pi over 8 plus square root of pi over 8i. And now we can compare. So this is going to be the integral from 0 to infinity of cosine of x squared dx. And this is for the integral from 0 to infinity sine of x squared dx. So now we have the value of our integral. Now what was it that we originally needed to find? We wanted to find this, right? So let's rewrite this at the bottom. We want to find root 2, the integral from 0 to infinity, cosine of t squared plus sine of t squared dt. This is now going to be root 2 plus, so we have root square root of pi over 8, square root of pi over 8. So we're going to say root 2. Oops, where did that go? Okay, we're going to have root 2 times 2 root pi over 8. And we can simplify this down to square root of pi.